And obviously, if you have any questions after the class, you can email me as well. So let's not waste any time and start with the first section or first lesson. So the first lesson in this module, microcontroller and digital electronics, is analog circuits. So you may have heard about microcontrollers before. And sometimes they are called as systems on a chip, because along with a processor, along with your processor, uh, the there are other things which allow them to control real equipments. So, for example, your microcontroller. Uh, so, for example, you have a microcontroller inside a car that can help with um, maybe operating the engine or the braking system. Then you have microcontroller inside your washing machines or your oven to control the temperature and humidity. So microcontrollers are used in all sorts of systems. So along with the processing unit, a microcontroller also has a memory, which is called as random access memory or RAM. Then they would also have some input output peripherals to connect your input and output devices. Then they also have analog to digital or digital to analog converters. Because most of the real world signals, they are analog in nature, right? They are continuous in nature. So to process them using a digital microprocessor, you will have to convert them, right? So you need an analog to digital converter. So these are all different things which are present inside your microcontroller. So we are going to look at a few basic analog circuit in this lesson. Not going to discuss about them in too much detail, or not going to cover the complicated stuff. We'll just discuss few of the simple analog circuits. And obviously, since we are simplifying things, so they might, the calculations, the formulas, they might not be very accurate. Okay. So the first thing we are going to look at is a current mirror. So it is basically a circuit which will allow us to have a fixed current even when some conditions are changed. So first of all, we'll look at some of the ideal current and voltage sources. something like a battery, which should give you a constant voltage irrespective of the current. So ideally, your battery should give you a constant voltage, no matter what is the amount of current. Right? Similarly, an ideal current source should have a constant current, no matter what the voltage or the supplied voltage is. Right? So this is the ideal current and voltage source. They should give us constant value of current in case of ideal current source, and if it is an ideal voltage source, I should get a constant voltage irrespective of the input or the output resistance. We should always get a constant value. But obviously, this is ideal, this is not practical. So, in real life, the voltage source will tend to give us smaller voltage when the current becomes large. Something like this. So, as and when the current increases, the voltage tends to drop. Right? It's because of the internal resistance. So we all know Ohm's law. So if we increase the current, the voltage will reduce. Right? Similarly, for a real current source, because of internal resistance in parallel, uh, to have a bigger voltage, the current will decrease by a small value. Okay. So if you increase the voltage, the current will tend to decrease by a small value. So this is a problem that we don't get constant voltage and current. Now, how can we get an near about constant voltage? So one way is to use a transistor. On the slide, we have the transistor characteristic, which you might have seen before. Usually you have like multiple curves, right? So something like these kind of curves, right? One above the other for different value of base current. But in this slide, we will only have one curve. Okay. So as we have seen, the collector current is almost constant. So in the transistor characteristic, this collector current is nearly constant, although it's slight sloping upwards, but near about it's almost constant for a range of collector to emitter voltage, as long as we are in this region. So this is called as the active region. So as long as we are operating the transistor in this active region, the current, the collector current IC, will be approximately constant, no matter what is the value of collector to emitter voltage. Right? So basically, we can use a transistor as a current source. But this is also not good enough. Right? You can see there is a slightly, it increases. There is a slope. So how can we make it even better? We can make it better by using a circuit called as current mirror circuit with two identical bipolar transistors. So for example, you can have BC548 or 549, but both the transistors, if you are using BC548, both of these transistors should be the same. Okay. So for implementing this current mirror, we have to use two bipolar transistors of the same type. The input current, it is coming from this VCC supply. Okay, so input current is coming from this supply voltage VCC, and it's going through this resistor R. So this resistor R, it is fixed. It has a fixed value. Now, so this is the base, sorry, uh, this is the base, this is your collector, and this is the emitter. So since we have connected the base and collector together for the first transistor, it's going to act like a diode, right? So we have another transistor here on the right hand side, which has to be similar to the first one. Now, although you can see a gap here, but in the actual circuit, we will use a resistance. Right? Obviously, if there is a gap, there will be no output current. So we have to connect an output resistor. So what would happen is, if you change the value of your output resistance, even then your current will not change. In the case of current mirror, you will always get the same value of current even if you change this output resistance. Okay. And why is it called as current mirror? So mirror is used to see the reflection, right? So if you stand in front of a mirror, you see a reflection of yourself. So this circuit is called as current mirror because it mirrors the input current. So whatever the value of input current you are applying, the same value you will get in the output, right? And it will remain constant no matter what is the value of your output resistance. Okay. So in brief, I can say V out will be equal, or it will be the mirror image of your input, and V out will be constant irrespective of R out, output resistance. Okay, so this is your current mirror circuit. Now we will look at it on multi-sim. Okay, so I have implemented this circuit on multi-sim, and this one. Okay, so this is your current mirror circuit. Okay, so you got your two transistor, Q1 and Q2. So I'm using 2N222A. So this type of transistor is very common, one of the very basic transistors. And this is your supply, V1 of 12 volts. R1 is your input resistance, and R2 is your output resistance. And we are going to measure the currents flowing in this circuit. So XM1, so this one, it will show us the input and current, and XMM4, so this multimeter, it will give us the output. Okay, there is one thing more which I want to show you or discuss. For that, we'll have to look at the data sheet of the transistor. So if I go back to Brightspace, you can find the data sheet for this transistor 2N222A. Okay, so mainly in this data sheet, we are interested in the current gain. Okay, so current gain is the factor that we multiply with the input current to get our output current. That means how much amplification you are getting in the output, or how much your transistor is amplifying the input. Right? That factor is called as current gain. So we are interested in small signal current gain. So basically we'll be applying a small AC signal at the input, and how much of a amplification we'll get in the output. So we can see, or in the circuit we are applying a DC voltage. So we will be interested in this one, DC current gain, not the small signal current gain. So DC current gain, again, it depends on the value of collector current. And it's just trying to zoom in, but I hope you can maybe see it. Let me just go in it like that, so that it is more clear, a little bit more clear. So we are looking at the DC current gain because we are applying a DC voltage at the input, and we are interested in how much amplification or gain we will get at the output. So that DC gain, it depends on the value of IC, the collector current. So if your IC is 0.1 milliamperes, your current gain, the minimum gain, will be 35, and the maximum you can get is 300. Then if your IC is, let's say, 10 milliamps, if you increase that, your current gain will increase to 75. So you could have a gain anywhere between 75 to 300. Okay. Now let's verify that in multisim. So if you double click on the component and go into edit components, so it gives you HFE min. So that's your minimum current gain. So sometimes we use beta for current gain, right? But in the data sheet, they use HFE. So capital FE is for DC and small fe is for AC. Okay, so it's again 35 to the maximum value is 300. Very similar to the data sheet. Okay. Now let's have a look at the input and the output currents. So my output resistance is 50 ohms and the input current which I'm applying is 20.16 milliamps. The output current which I'm getting is close to the input but slightly more. I would say 1.51 milliamps more. So we are getting 21.67 milliamps as the output. So ideal current mirror should give exactly the same value as your output current. But obviously we all know this is a practical circuit. So you won't get exact value, but they are close enough. Okay. So first thing about current mirror, it gives the same value of input as your output. Now, second thing is if we change the value of output resistance, this value should not change. It should not change much. So let's stop running the circuit. Let's change it to maybe double the value. So, oops, sorry, 100 ohms. So instead of 50, now we have 100. So ideally in any other circuit, the current should reduce by half, isn't it? You are doubling the resistance. Let's see what happens in the current mirror. It went down a little bit, but still it is fairly stable, like 21 from 21.6. It's now about 21.5. So near about the same output current we are getting. Now how about we change it a little more, maybe a 200. Oh, maybe 200. And let's see. Again, it fell a little bit, but it's around 21.15. Right? So it's again fair, I would say fairly constant output current. Now, every circuit has a limit. Let's now increase it to maybe 500. Let's see. Let's check the limit. Um, Quite close, like 20.16 and 20.166. So quite close enough. And so still, I think this is the limit. Maybe 500 is the limit. Now, if I increase it to maybe 1,000 ohms, the output resistance, um, yeah, it fell down, like it's 11, 12 milliamps. So let's check for smaller value. Let's decide the range, maybe for um, 10 ohms. Let's see if it is 21.8 approximately. And if we change it to maybe 1 ohm, and yeah, so ideally, like we can say that between 1 ohm and 500 ohms is the limit, is the range of resistance, right? So between 1 ohm and 500 ohms, you would get this like similar value of current, right? Now, another thing which I want to do is calculate the value of current gain. So we got the ammeters connected. We can calculate the current gain. So this is the output, and this is the input for Q2. For Q2, this is measuring the input, and 4, XMM4 is measuring the output. So output divided by input, it will give me the current gain for this transistor Q2. Now before I do that, I want to change it back to 50, the original value. Okay, let's not worry about this one. So my output is 21.67 divided by 97 this is the input for Q1 and the out. So we are getting 21.67 milliamps as the output divided by 5 microns. So roundabout I'm getting slightly off 50 ohms. But yeah, roundabout I'm getting 222.7 as the gain for Q2. Let me calculate the gain for Q1. So it's 20.16 divided by 98. It's getting 204. Although I don't know, maybe slightly it is why this is slightly off. Ideally, both Q1 and Q2, they should have the same current gain. Let me just double check. not all empty, but yeah. So yeah, so 204 for Q1 is the current gain, and 227, I think I calculated, is the current gain for the Q2, 222.7. Ideally, they should have the same current gain. I don't know why, but I'm getting a slightly different value today, although the settings are correct. But anyways, slight difference. Probably that's why we are getting a different value as the output. Right. So this is your current mirror circuit. And let's come back to the slide. Okay. So beta is your current gain. In the data sheet, they use HFE. Okay. But for us, we'll use beta as the symbol for current gain. So let's say, so this is your current mirror circuit. So let's say the current going into the base of the transistors, of the two transistor, is unity. It could be either 1 milliamp or 1 microamp, doesn't matter, just for the concept. So let's say it is 1 milliamp. Okay, so 1 milliamp is going into the base of the two transistors. So we need 2 milliamp coming in from here, right? So then only it will get divided 1 and 1. Okay, so we have 2 milliamp. Now at the collector terminal, the current should be beta. So your gain for the transistor is beta. So at this terminal, it should be beta. So altogether, beta plus 2 should be your input current, right? And then you have beta here and 1 here. So altogether at the emitter side or emitter current, it should be beta plus 1, and this should be also beta plus 1. So the output current for both the transistor should be beta plus 1. Sorry, it should be the output current, or the current coming from the emitter side. It should be beta plus 1. So your output current, it should be beta for both the transistor or for this circuit. Right? So therefore, the transfer coefficient, which is the ratio of the input current to the output current, will be beta divided by beta plus 2. Right? So if we know the value of beta, we can calculate the ratio, the the output current divided by input current. We can calculate this if we know the value of beta. Also, if we look at the left hand side of left-hand side transistor in the previous circuit, the input current is equal to the supply voltage VCC minus the base emitter voltage divided by the resistance. So if we go back to the previous circuit, the input current, we are talking about this current, input current, it is basically VCC minus, so you will, since you have connected the base and the collector terminal, you won't have any voltage drop here. All the current will go directly to the base. So the only other voltage which you will have is between base and the emitter. Okay. So VCC minus base emitter voltage divided by the resistance R. So that will give us the input current. Okay. Now, since the base and collector, they are connected, so the only drop in voltage, the VBE, this value, the base emitter voltage, it would be approximately like 0.6 to 0.7 volts. The base emitter voltage drop will be about 0.6 to 0.7 volt. Now your transistor, basically to explain it, your transistor, it is a 3-terminal device and you are connecting the base and the collector together, right? So all the current flowing into the collector will directly, there is no junction, right? You have this P and P transistor, right? So if you have connected them together, all the current will directly flow to the second junction. So in a way, it acts like a diode, NP diode, and the voltage drop across a diode is between 0.6 and 0.7 volts. That is why the base emitter voltage, I am saying it will be between 0.6 and 0.7 volt, because you have connected the base and collector together. Okay. Now here is an example on current mirror. A similar kind of question can be asked in your exams. So we are given with the current gain HFE or beta. It is given as 90. It's the same for both the transistors in the current mirror circuit. Okay. Now the supply voltage VCC is given as 9 volts. And we have to calculate the value of resistance R. Give an output current of 200 milliamps. This is my output current, I out. So we have just now seen two formulas. We can use them to calculate the value of resistance. Right? Shouldn't be too difficult. So the first formula which we have seen is I out divided by I in is equal to beta divided by beta plus 2. Now the output voltage, output current, I out is 200 milliamp. So it will be 0.2 amps. Okay. So just if you substitute, like if you rearrange this equation to find out the input current. So I in will be I out multiplied by all of this, beta plus 2 divided by beta. And if you substitute the value, so I out is 0.2, beta it was given as 90. 90 plus 2 divided by 90. So you would end up getting 0.2 amps as the input current. Now, one way to verify it, the input current and the output current, they should be close enough. It's a current mirror circuit. They should have a similar value. Okay, so we are getting 0.204, slightly more. Then, from the second formula, we can calculate the value of resistance. So this was the formula. And from there, if you rearrange the formula to calculate R, you will get VCC minus VBE divided by I in, the input current. Now, in this calculation, I have used VBE to be 0.65. Okay, this is VBE. In exams, you can use any value, 0.6, 0.65, or 0.7. So any value between 0.6 to 0.7 will be correct. Okay. Over here, I've used 0.65, but you can take any values between 0.6 and 0.7. Okay, it will be considered as correct. So I am getting 40.84 ohms as the resistance. Right. Quite simple, and I would say a classic exam question. Right, so the transistors, there are some assumptions which we make. The transistors are identical, although we know that in real scenarios or in practical circuits, you can't have two transistors exactly the same, right? Even if they are coming out from the same factory, same batch, even then the two transistors will be slightly different. They will have slightly different current gains. Okay. But for calculation, we assume the two transistors to have the same current gain. And the voltage drop across base emitter, we have assumed the value to be 0.65 volts. Okay. Now, one thing can I can show you here. I don't know if you noticed is let me go back. So my output current was 0.2 amps, and my input current is coming to be slightly higher than the output current in this calculation. But in the circuit, so this is my input current, right, which is smaller than the output current, right? In the Simulink circuit or in the multi-sim circuit, my output is slightly more than the input. But in the calculation, we are getting the other way around. So this shows that the formulas or the calculations which we are doing, they are simplified, right? So it doesn't give you a very accurate value. It only gives you an estimate. Okay. So the calculations, all the formulas, they are not very accurate, but it will give you the estimate, the idea that how much the resistance should be or how much the input and the output current will be. Okay. So we can make them better and avoid the mismatch between two transistors by connecting resistances. So in practical circuits, you may have two transistors which are not very well matched because, as I mentioned, even if the two transistors are coming out from the same patch, from the same factory, they will have slightly different current gain. So to adjust or minimize this mismatch, what we can do is we can connect two resistances. We are not going to spend a lot of time, discussing it, but yeah, we can do that. And another thing using current mirror circuit, which we can do is we can produce multiple outputs with slightly different values. From the same current mirror circuit, we can produce different values of output current. Okay. The next thing is your differential amplifier. It is also called as long-tailed pair. And the circuit is shown in the slide. You might remember that op-amp are differential amplifier. And basically, this is the building block of an op-amp. Now, the idea is that we have two identical transistors, okay, each with different input voltages, V in 1 and V in 2. However, the two voltages, they are quite close. There is a very small difference between the two voltages. And we want to amplify that difference. So we will get two output voltages. Again, different, but with bigger difference, right? So we can use this circuit to measure small differences. We can amplify the small differences and measure them. An example of this, of of the use of this circuit would be something like in sensors. So maybe your sensor is measuring temperature. So if you use this differential amplifier, it can, identify or detect very small changes in temperature, right? So small differences can be amplified using this circuit, and the measurement will be much more easier. Now at the bottom of this circuit, we have a constant current circuit, which could be a current mirror with a constant RT resistance. So this circuit is called as long-tailed pair, and this is the tail of this circuit. Okay. Now we'll ignore the theory of this circuit, or we'll not study too much about the working of the circuit. And we'll straight away come on to the formulas or some of the parameters in the circuit. So we have something called as differential gain, which is the difference in the output voltage divided by the difference in the input voltage. And a good differential amplifier should have high differential gain. Okay, so differential gain, you can understand something like how much amplification or how much your circuit is amplifying the difference, or how much gain you are getting for a difference. Right? Differential gain, right? So how much is the circuit amplifying the difference in the input, right? That's your differential gain. And ideally, a differential amplifier should have high differential gain. And we can get the differential gain in terms of different of these parameters. So small signal current gain beta, RC is your resistance connected to the collector, and RBE is the resistance between the base emitter, right? So it's an inverting amplifier. So you get a negative sign here. So it shows that it is an inverting amplifier. That's why you get a negative sign. It will amplify your difference, but it will invert it. So if you have a small difference, it will amplify it, but invert it. Something like this, right? Quite similar to op-amp. It is the building block of op-amp. Now, the other gain, which is not so good or not very desired, is the common mode gain. which we don't want. So if you remember, in case of op-amp, we have noise which may come from either transformers or switches, which produces electromagnetic interference at both the inputs. So the amount of noise at both the inputs the amplifier amplifies is called as common mode gain. So common mode gain is the amplification to the signal common to both the input. Okay, this is a differential amplifier. We want to amplify the difference between the two input signal, right? And if you get amplification for a common signal, common between both the input, if your amplifier is amplifying it, it's undesired. We don't want that. Okay. So common mode gain, it should be as low as possible, right? A common, a signal common to both inputs would be noise, right? So noise can only affect both the signals equally. So ideally, my amplifier should get rid of this noise. It should reject this common signal or common noise to both my inputs, right? So we want RC to be as big as possible and RT to be as small as possible. Right? Now, in any differential amplifier, we will have both the differential gain and the common mode gain. And what we can do is we can combine them together to find the CMRR, the common mode rejection ratio. Okay. Now it is measured, it is basically measure of how well the amplifier rejects a signal or a noise which is common to both the inputs of an amplifier. Rejection ratio, common mode rejection ratio. So how well your amplifying is rejecting the common signal or noise at the input side. Now it is given by this formula. So again, you can divide the differential gain by common mode gain. And if you calculate, you will get this formula. Beta RT divided by RBE. Okay. Now, to improve the output performance, we can again add two resistances and we will get a new set of formulas. Although I will not worry too much about it because you don't have to worry about the formula, this formula, because it will not be asked in the exams. I think only these formulas, these basic formulas, if you remember, differential gain, common mode gain, and CMRR. These three formulas you will have to remember. It will not be given in the formula sheet. So you will have to remember the formulas. This one is not important. Okay. Now let's take an example. So in this example, based on differential amplifier, we have two well-matched transistors. So they would have the same current gain, right? So they have a small signal current gain beta. So beta for both the transistors in your differential amplifier is 170. And the base emitter resistance is RBE. It is given as 65 ohms. Which is the same for both the transistors, the base emitter resistance. Now, if RC, it is 560 ohms, and RT, it is 4.7 kilo ohms. We have to calculate the differential gain, the common mode gain, and then we have to calculate the CMRR in decibels. Okay, so all the values are given. We already know the formulas. We just have to calculate them. So let's quickly go through solution. So differential gain, it's given by minus beta RC over 2 RBE. So you know all the formulas, all the values. So beta is 170 RC, it is given as 560, and RBE, it is given as 65. Okay, RT, it is 4.7 kilo ohms, and RC is 560, I've already mentioned. Come on. Yeah. Right, all the values they are given, we just have to substitute them. So if you substitute the value, we get a negative value here. Okay, so this is just a number. You have calculated differential gain, but it will be just a number. And gain is usually represented in dB, decibels. So we will have to convert this number into decibel. So while calculating the value in decibel, we ignore the negative sign. Okay, so we ignore the negative sign, right? So you can simply calculate is like you can take log base 10 of this value, multiply it with 20. I'm getting it as 57.29 dB. Then common mode gain, again substitute the values. Remember this is 4.7 kilo ohm, so it will be 4700 ohms, right? That's the value. Again you get a negative value, so you can ignore it while calculating the decimal equivalent value. Okay, so while calculating or converting the gains to decibel, we ignore the negative sign. But since this number is less than 1, we have 0.06 approximately. So if you take log of that, you will get a negative value. Okay, so ultimately we are getting minus 24.5 dB. So the common mode gain is quite small, about like 0.06, which is good, right? Ideally, we want it to be 0. The differential amplifier should not amplify any signal that is common to both the inputs. Ideally, it should be 0, but practically or in the calculations, it should be as small as possible. Now, the last thing we have to calculate is the CMRR. So again, you have the formula, substitute, get this value, and then convert it into decibels. So in decibels, we are getting 81.8 dB. Okay. Now, one way to check your value for CMRR is if you calculate the difference between uh, differential gain and common mode gain. If you subtract them, you should get the same value. So 81.79 dB. So this is one way of checking your answer. So again, this type of question is quite common in exams. You will have to remember all the formulas, the 3 formulas. Right. There are a lot of techniques that are used in the manufacturing of an integrated circuit to make them more efficient and use less power. So if we want to build a differential amplifier on an integrated circuit on a chip, we will try to avoid these resistances, because these resistance, they kind of waste the current. So therefore, we can use a transistor to implement the resistor, and we have the same we have something called as active load. So active load is basically resistances which are implemented using transistors. Okay, but you don't have to worry too much about this. You don't need to know the formula or the working for this. Now, this is your super beta transistor. It's a little interesting. So basically, in here or in this figure, you can see that we have 2 transistors connected back to back like that. So this is your super beta transistor. So in this, let's take an example here. So let's say if you are supplying 1 amperes to the base, right? And the first transistor, it has a current gain of beta. So at the emitter, you will get beta plus 1, right? So this will be the output. Now, if you connect another transistor to the emitter of the first. Then the input to the second transistor is now beta plus 1. Now, ideally, the input current is higher, so you should have a different type of transistor. But just for discussion, if we say that this transistor, the second transistor, also has the same current gain beta. So in that case, you would get something like 1 plus beta times beta plus 1 plus beta. Right? This will be your output. If I quickly try to simplify it, it will be 2 beta plus 1. Now, if, for example, if we say beta is 100, so beta square will be 10,000 volts. So you can see, like, from 1 volt to 10,000 plus more than 10,000 volts you will get by using super beta transistor. So these are used in the circuit to provide amplification. Okay. And that's called a Darlington pair. And the symbol, so this is the symbol of a super beta transistor, or you can say a Darlington pair. Right? So it has 3 terminals. In comparison, quite similar to the normal transistor, but they are slightly bigger. The next thing is level shifting. So level shifting, it means adding or subtracting a DC component to a signal. Shift the level either up or down. Right? So we could do that by using our voltage divider, this circuit. So this is your voltage divider by using two resistors, right? So as mentioned earlier, we avoid using resistors in an integrated circuit. So what we can do is we can replace the two resistors, and we are going to end up using multiple transistors and diodes like that, which is quite complicated. Instead of using a single component, you are using multiple transistors and diode to implement a single component resistor. But yeah, that makes things more efficient, use less power, right? On the integrated circuit, power consumption is quite important. So that's why we do use quite a lot of transistors and diodes to implement the two resistors and build a level shifter. The next thing is buffer. So a buffer is when we want a high or a large input impedance. Right? So it can stop current being transmitted from one input to the output. So what we are doing is that we are connecting our output to the emitter of this transistor. So this is your voltage like level shifter, and you are connecting the output to the input of this transistor, right? And this is a common collector amplifier. So normally we connect the output at the collector. So output is collected from the collector side, V out, which is your common emitter amplifier. So you apply the input here to the base emitter, and you collect the output from the emitter side. So that kind of introduces a very large input resistance. Right? It would act like a buffer. So basically, we can implement a buffer using transistor connected in this configuration. Now, if we put these things together, we can get a basic op-amp, operational amplifier circuit. So in an op-amp, we will need differential, we will need a differential amplifier, which will calculate the difference between the two input signal. Then we will need a super beta transistor, or your Darlington pair, to amplify the difference and provide more gain. Then we are going to have the output buffer to have high input impedance, okay, and low output impedance. So this is the basic building block of an op-amp. Now, if you look at the circuit, this is the circuit of an op-amp, and you should be able to identify some of the parts. This is your super beta transistor, and you have the current mirror, and like this is your differential amplifier, right? So you can recognize some of the parts. The circuit of a real op-amp is more complex, but this will not be asked in the exams. Now there are a few more circuits we can look at. The first circuit is your peak detector. It's basically it's going to give us a DC output depending on the input. So the usual input is a square wave, which is then connected to your op-amp, and then you have a Schottky diode and a transistor, which is connected in common collector mode. The output is a DC value of the peak input, voltage across this Schottky diode. The base emitter voltage of the so this is your output here. So output is basically the peak input minus the voltage dropped across this Schottky diode minus the voltage drop across the base emitter junction of this transistor. So it kind of detects the positive peaks in the supply or in the input. The next one is your current monitor. The idea is to measure the current. But for that, we need to connect an ammeter. And to connect an ammeter, we will have to break the circuit. Right? You'll have to disconnect, put the ammeter in, and then connect the two terminals back to the ammeter, which sometimes it may not be desired. Right? So this is an interesting circuit, and we can have a look at it in multi-sim. So what we can do is, instead of using the ammeter, we can use a voltmeter, and that voltmeter will give us the same number in volts to what is your current, right? So instead of amperes, the voltmeter will give us the value in volt, the same number, right? Let's maybe quickly close all this, and we can have a look at this. So this is your current mirror, not current mirror. This is your current monitor circuit. Yeah, current monitor circuit. So, we are not much interested in the working, but I can maybe quickly show you the. So this is your ammeter, and just over here you have your voltmeter, right? And the idea is that the voltmeter should give me the same number as the ammeter is giving, so that I can simply disconnect this ammeter and use the values. Just have to, instead of millivolts, I will have to use milliamps. Okay, so your resistance is currently set to 50% of 100 ohms. It's near about giving the same value. So your current is 179.6 milliamp. We are getting 180.8. If you change the value, still they are quite close enough. 196, 199, right? So you can change the output resistance. It still gives you the value quite close to your ammeter. So this circuit can be used to replace ammeter. So instead of using ammeter, you can only use voltmeter and use the same number. Okay. Now I'm aware about the time, so there are a few more circuits like logarithmic amplifier, and then you have automatic gain controller. So I'm not going to discuss it in the class. There is a detailed discussion in the lecture notes. So if you are interested, you can find more information about all these circuits in the lecture notes. You can also try them and implement it in multisim. Okay. Multisim, I'm using the installed version, the desktop version. You can also use the online version. If you want, you can maybe search multisim online, and you will have to create a profile in multisim using your UHI account. Okay. And that way you can use the online version. You don't have to install it. If you want to try, you can use that. But the main thing for exams are I will write it down, the current mirror, and the differential amplifier. And sometimes you may get questions on maybe Darlington. Pair, or your super beta transistor Darlington pair. So these are the three important topics in for your exams. Okay. You can practice a few questions. They are there in the tutorial and MCQs section. So I would recommend you all to practice questions from there. Okay. So I will stop the recording now. And